video we're going to start section 3.3, and that is just some new derivative rules, and we'll talk about higher order derivatives. In this section we're going to concentrate on a couple rules. Two of them are the product rule and the quotient rule, and then we'll find the derivative of the rest of the trig functions. We found sine and cosine in the last section. We'll do the rest of the trig functions, and then we'll just talk about higher order derivatives, taking the derivative of a derivative. But in the last section, this would be a 3. In 3.2, you learned that the derivative of a sum of two functions is simply the sum of their derivatives. Like here we have x to the third plus, or that could be a minus 2x squared. Because, this is a sum or a difference, and we just have these individual functions here, we can just take their derivatives separately. 3x squared plus 4x, and that would be the f prime, and that just works for sums and differences. If we have two terms that are multiplied together, then we're going to have to use the product rule. The rules for the derivatives of the product and quotient of two functions are not as simple as, this sum or difference rule. So here we got theorem 2.7, the product rule. The product of two differentiable functions. Our functions are named f and g. The product is itself differentiable. Moreover, the derivative of f times g is the first function times the derivative of the second, plus the second function times the derivative of the first. So here's our notation. d dx, we're taking the derivative with respect to x of two functions multiplied, f of x times g of x. And that derivative is equal to the first function, f of x, as it was originally written, times the derivative of g prime, plus, it's always plus, and the second term is g of x, the original g of x function, times f prime of x. So it's the first times the derivative of the second plus the second times the derivative of the first. And the good thing about that, if you get that backwards, because this is a sum, because that's a plus, you could get that backwards and you'd still get the right answer. Oops. So here's an example. Example 1, find the derivative of this function h of x. We have 3x minus 2x squared is one term, and the other term is 5 plus 4x. And here's how I like to do this. This is the way I've been doing it since I was in calc in high school years ago. When I have my two functions, I'm going to draw like a little double arrow coming down here to find its derivative. The derivative of 3x minus 2x squared is 3 minus 4x. And then the other term here has a derivative of, well, the 5 derives away to nothing, and the derivative here is just 4. So I'll underline in red, these are the functions, sort of call them f of x and g of x. And these are the derivatives, f prime and g prime. So I want to find the derivative here, and they're calling this function h. So our derivative will be h prime of x is equal to, and the product rule tells us we have to do first times the derivative of the second plus second times the derivative of the first. And the reason I started doing this when I was in high school, it almost looks like a cross-multiply problem. If I'm looking at the first function times the derivative of the second, I'm sort of multiplying across on this diagonal. First function and the derivative of the second. So this is going to be quantity 3x minus 2x squared. That's my first function times the derivative of the second is 4. Plus the second function, and now I'm sort of cross-multiplying on the other diagonal. 5 plus 4x times the quantity 3 minus 4x. So this is the derivative sort of in the raw form. What we can do is clean it up a little bit. We can distribute this 4 across the parentheses. We can FOIL this second term out and then collect up all our like terms. So I'm going to switch over to blue to start that. Let's see, distribute the 4 here. It looks like we're going to have a 12x minus 8x squared plus, and here we're going to FOIL this out. 5 times 3 is 15. 5 times minus 4x is minus 20x. And then our inner terms are going to give us a plus 12x and then a minus 16x squared. And I guess since this is a plus here, it's not like we have to distribute a negative or anything. I can just drop those parentheses. I never needed them in the first place. And now we can just collect up our like terms, and our end result there will be our final and pretty derivative, h prime of x. So let's see, our squared term is the biggest. Here we have a negative 8x squared. Here's a negative 16x squared. So that's a negative 24x squared. And then our x terms, 12x, and another 12x is 24x, and a minus 20x leaves us 4x, plus 4x. And then we have a plus 15 at the end, plus 15. So there's our derivative h prime of x. There was a little bit of work there to get to it, just some more algebra than calculus. So there was a little work involved in that. Is there an easier way to get that same answer? Or another question would be, did we have to use the product rule in this case? We did have two terms that were multiplied together, and since our problem was set up like that, that is one route to go. Use the product rule that we just learned in the last slide. Or there's another way here. We can get by without using the product rule. From the very get-go, we could have foiled this out. So our h of x, I'm just going to FOIL here, is 15x plus 12x squared minus 10x squared and minus 8x to the third. And I can combine, I'll put my leading term, my third power, 8x to the third negative. My squareds, I'm going to leave that with a plus 2x squared. And then we have our 15x plus 15x. And now that we got rid of the product part of the problem where we're multiplying these two binomials together, this is still h of x. It just looks a little different. Now we can derive it and get h prime of x. Well, 3 times the negative 8 is negative 24. X to 1 power lower, that's now squared. Then we'd have a 4x deriving the middle term, and the last one, the x would derive off, and we're left with 15. Exact same answer. I believe in this case, the second way, foiling this out first and then deriving, was the easier path to take. But we can do the product rule there too. Example 2. Here, the product rule, we could write it right here in the notes. Example 1, you could write product rule optional. Product rule optional. We didn't have to use the product rule, but we could. Here, product rule is necessary. We must use product rule. Must use product rule. No way around it. Because if we look at this function we have here, find the derivative of y equals 3x squared sine of x. And it's real easy to just confuse that, make it look sort of like one term, and you want to do the 3x squared to be a 6x, and the derivative of sine is cos, and you think you're done. I always like to just underline these little brackets. My first term is 3x squared. My second term is sine x. Those are two distinct functions, so we are going to need the product rule. And the derivative of 3x squared is 6x. And the derivative of sine is cosine of x. So we're going to find the product, or the derivative, using the product rule. We'll use prime notation. Y prime equals first times the derivative of the second. That would be 3x squared times the cos of x. And then it's always plus. Second times the derivative of the first is going to be 6x times the sine of x. 6x sine x. And if you left it in that form, that is it is correct. We could, if you noticed here, we have some terms that we might be able to factor out. A 3x squared and a 6x. What's the common factor that we can pull out of each of those terms? Well, we could pull out a 3x. So if we pull a 3x out of here, we're just left with an x times the cos of x. Plus we pull a 3x out of here, we're left with a 2 sine x. And there we go. Okay, here's our last example for the product rule. Find the derivative of y equals 2x cos x minus 2 sine x. Well, first thing you need to figure out is, where do we need the product rule? Well, this second term here, that's just a constant times sine x, so that's not the product rule part of the problem. But right here we do have a product. 2x is one of our functions, and cos of x is another function. So this piece, we're going to have to use the product rule on. I'll just abbreviate PR. And then this term, will just be along for the ride. We'll derive that, after we get this product rule part figured out. So let's see here. The derivative of 2x is 2. The derivative of cos is negative sine x. So we have y equals, so we'll use let's change it up. dy dx. We're deriving the y function with respect to the x variable. So first times the derivative of the second, sort of along this diagonal, negative 2x sine x. Put the negative first, negative 2x sine x, plus second, or times the derivative of the first, 2 cos x. And then we have this term come along for the ride. Then we're just going to derive that separately. Minus the derivative of 2 sine x is 2 cosine x. Oh, look at that. It looks like it'll simplify down a little bit. We have a 2 cos x and a minus 2 cos x, so those are going to wash out. And we're left with our derivative dy dx is equal to negative 2x times the sine of x. Okay, now this product rule, it doesn't work on just the product of two things. The product rule can be extended to cover products involving more than two factors. For example, if you have three functions, f of x, g of x, and h of x, and they're all differentiable with respect to x, then, see here we have a triple product. The first one times the second one times the third one, f, g, h. And to set up the derivative, you're just going to write this out. There's three of these functions. You're going to write it out 3 times, f, g, h, f, g, h, f, g, h. And then in each term, each function has a term being the derivative. Here first it is the f function is derived, f prime x. In the second term it is g. In the third term it's h. So each term has a derivative in it at one point. And you know, you could expand that to 4 functions multiplied together, 5 or 6, and just keep right on going. Now the other rule, the major one we're going to talk about in this video, is the quotient rule. Theorem 2.8, the quotient rule. If the quotient f divided by g of two differentiable functions, f and g, is itself differentiable at all values of x for which the derivative, or the denominator, g of x, does not equal 0. Moreover, the derivative of the quotient f divided by g is given by the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. So that's quite a mouthful. There's an easy way to remember this. Here is our quotient, f of x divided by g of x. We're taking the derivative with respect to the x variable. And here is the derivative. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared, as long as g of x, that denominator, does not equal 0. And here's the easy way to remember it. We have our quotient f of x and g of x. Up here, the one on top, we can call that the high function. And the one down here in the denominator, the bottom, is the low function. So we have our high and low, and if we want to do this quotient rule in terms of that, we're going to have low d high minus high d low all over low low, or low squared. Low d high minus high d low over low low. If you get on YouTube and look up quotient rule or quotient rule song, I'm sure you're going to find a bunch of videos of students have made on the quotient rule and coming up with a little song or ditty to remember the order of it. And on this, it is important to have that numerator in the proper order. The product rule, it didn't matter because this was a sum in the middle. Here it is a difference. We're subtracting. You cannot get those numerator terms reversed on the quotient rule. So let's take it for a test drive. Find the derivative of y equals this. So we're going to find y prime. And our numerator function is 5x minus 2. The derivative of that is a nice easy 5. Our denominator, or our low function, is x squared plus 1. That derivative is 2x. So we just plug it into the proper place in our quotient according to the jingle. Low d high. Low d high. So it's going to be sort of cross multiplying on this diagonal. 5 times the quantity x squared plus 1. So that's so we have low d high minus high d low. sort of cross multiplying on the other diagonal, and I'll put my single term out here. The 2x, I'll make that negative, and the 5x minus 2 in parentheses. So low d high minus high d low over low low, the denominator squared. X squared plus 1 quantity squared. Now, in a lot of these calculus problems, we are going to distribute and try to clean up that numerator a little bit. Don't FOIL this out. That's sort of making the problem a little more complicated. If we have this binomial squared, we could replace that with, x to the 4th plus 2x squared plus 1, but that's sort of taking it a step in the wrong direction. So again, let's work on our numerator a little bit. Let's distribute the 5 and the 2x across those parentheses. So at first here we're going to have, 5x squared plus 5. And then distribute here, and don't forget we're distributing the negative also, so that's going to be negative 10x squared plus 4x all over low low, our denominator squared. And it looks like we can combine some stuff in the numerator still. Our x squareds will wind up with a negative 5x squareds when we combine our two terms, and then a plus 4x and a plus 5. And our denominator, looks like I can squeeze it in there, x squared plus 1 quantity squared. And there is the derivative of our original quotient. And again, don't lose sight of the big picture. If we were to graph this function, the original function, it would be a curve in the coordinate plane. And if we wanted to find the slope at any given x value, we would put that x value into our derivative and find the slope at that point, that instantaneous rate of change. Okay, let's move on to example 5. And it says here after example 5, rewriting before differentiating. So we have this function here, find the equation, and it does say find the equation of the tangent line of the graph at this point. I just realized in my notes from last year, I didn't take this problem all the way to the end and find the actual equation of the tangent line. We did find the derivative, but we just lost sight of the overall directions. And it says rewrite before differentiating. Our function that they're giving us is 3 minus 1 over x, and then over x plus 5. And I guess we could derive this. We could rewrite this as x to the negative 1 power and go from there. But there might be an easier way to do this, and that would be to clear those fractions. And there's only one fraction in the whole problem, and that's in the numerator. And to clear that fraction, we would multiply by its denominator. So I'm going to multiply through the numerator term by an x. And to make it fair, I'm going to multiply through the denominator by the same x. So here when we distribute, now our numerator is 3x minus 1. And our denominator is x squared plus 5x. So we didn't change it much. We made it look a little different. And now it's probably going to be a little bit easier to use the quotient rule on. So our upper derivative is 3. Our lower derivative would be 2x plus 5. That's a plus. And now we can find the f prime of x. So low d high, 3 times quantity x squared plus 5x. Low d high minus high d low. So here we're going to have our 2x plus 5 times 3x minus 1, all divided by low low, x squared plus 5x, quantity squared. Okay, so from here we would distribute the 3 across here. Here it'd be real easy to mess up with this negative sign. We want to FOIL these two binomials out and then distribute the negative across those parentheses. And then, like I said before, leave that denominator alone. And just for the essence of time, this is just the algebra that goes along with it. We should all have pretty sharp algebra skills at this level. When you clean this all up, it should look like our numerator is negative 3x squared plus 2x plus 5. And our denominator is still low, x squared plus 5x quantity squared. And again, I did mess up last year. That's where we stopped this problem and moved right on, and nobody caught me. because according to the directions, we're not done. It says find the equation of the tangent line to the graph of this at this point. So we could graph this. It'd probably have a curve somewhere there in the coordinate plane, and at the point -1 up 1, we want to know, I don't know what the graph even looks like here, maybe it's something like this or curving the other way, but we want to find the tangent line at that point. And remember, to find a tangent line, we need a point on that tangent line, and we need the slope of the tangent line. Two things. We have a point on the tangent line. We know this point is on the curve, and it's also where we want, or to be a point on our tangent line, and that is the actual point of tangency. So our point is -1, 1. We need the slope at this point. How do we find the slope at that given point? Well, remember here our x value is -1. If we plug -1 into the original function, that gives us this output of 1, the y-coordinate of the function. But we don't want that. We want the slope. So we're going to plug that -1 into the derivative. So we want to find f prime of -1. And that means we're just going to plug a -1 wherever we see an x. So this will be -1 squared plus 2 times -1 plus 5, all divided by -1 squared plus 5 times -1. So let's find our slope at this point. In our numerator, working in the parentheses first, -1 squared is 1 times -3 is -3. And then we're going to have a plus 2 times -1, so that's going to be a -2. And then we have a plus 5. And I don't think we have to go any farther, because if you look, keep going with that numerator, -3 minus 2 is -5 plus 5 is 0. So no matter what the denominator is, we're going to have 0 divided by something. And well, I guess that something's easy enough to find. This is going to be 1 minus 5, -4. So our derivative at that point, our slope at that point of tangency is 0. So we have our point, we have our slope, and we can write the equation of the tangent line. Now, if you can't see what this is going to look like intuitively, we can just go back and do this piece by piece. And our equation, y minus y sub 1 equals m quantity x minus x sub 1. Plug in our points, y minus 1, from here, equals our slope of 0 times x minus -1. So x minus -1 becomes x plus 1. That's all wiped out by the 0. So we have y minus 1 equals 0. Add 1 to both sides. Y equals 1. And that just makes intuitive sense. Here's our xy axes, and we have a horizontal line here at y equals 1. We know this point -1, 1 is on the graph, so over to -1, up to 1, there's our graph, or our point of tangency. And I guess the graph is probably going to be some type of curve up or some type of curve down, and that is our point of tangency. And our equation for a tangent line, it's in y equals mx plus b form, but there's just a 0 for the slope m. Using the constant multiple rule. Be careful. There's some problems you can do with the quotient rule, but they'd be a lot harder. If you can recognize, ripping out a constant, it makes it so much easier. Like here, you look at this first one, the quotient rule is fresh on your mind. You could say, okay, here's my upper function, and the derivative of that is 2x plus 3, and my denominator, my lower function, is just a constant, so the derivative of that is 0. And you could go through and do low d high minus high d low over low low, and you would get the right answer. It's going to be a lot of work, and the more work you have to do, the more algebra is involved, the more chance to make a very simple mistake and get the answer wrong. So here, if we look at this original function, that denominator that I focus in on is just a constant. So we can just sort of drag that out. When you drag it out, you don't drag it out as a 6. Since it's a denominator, you pull it out as a 1/6. 1/6 times the quantity, x squared plus 3x. And now that we pulled that out of there, it's a lot easier to see. This is just going to be a nice, straightforward derivative. The 1/6 is a constant. So we can just pull that out and take the derivative and put it back. So we have our 1/6. The derivative in here is just a simple sum. Derivative of x squared is 2x. The derivative of 3x is 3. And I guess if you want to give it back in the form that they gave it to you, and here that 6 was in the denominator, and we pulled it out in the first step, I guess we could put it back down there. That'd be nice. So we could leave this as 2x plus 3 over 6. You know, on a test, I would take this in a heartbeat. You don't have to put it back in there like that. Letter B, we have 5x to the 4th over 8. Again, because there's no sums or differences in that numerator and denominator, we just have these constants, we can just pull that out front. Y equals 5/8 x to the 4th. And now we can just derive it. Y prime would equal, y prime equals, bring this down and multiply that by the term that's already there. 4 times 5 is 20. 20 over 8, x to 1 power lower, x to the 3rd. And I guess we can factor out a 4 there. So that would be 5 halves, x to the 3rd. All right, letter C. Ooh, this looks a little more complicated. We have negative 3 times a quantity over 7x. And sort of like what we did here in B, we can do down here also. You know, this negative 3 is multiplied by this term in parentheses, and we just have the 7x by itself. So that means we can pull these constants out of there. That negative 3/7 can come out. Negative 3/7. And then we have our fraction. Now the denominator, there's just an x down there. And up top, we have a 3x minus 2x squared. Ooh, now look at that. Since we pulled the 3 and the 7 out, it becomes a little more obvious that an x will cancel. We have an x in the denominator and an x in each term that remains in the numerator. So this x is going to cancel out with this one. And it's going to cancel out with one of these two x's that are multiplied here in the x squared. So that'll get knocked down to an x to the 1st. So now we just have negative 3/7 times the quantity 3 minus 2x. And now we haven't taken the derivative yet. You know, I've gone a little past. So we are going to take the derivative now. Y prime equals constant multiple. The negative 3/7 stays. Derivative of the constant is nothing. The derivative of minus 2x is minus 2. And then we can just multiply those together. Negative 3/7 times minus 2 is 6/7. Okay, one more example here, and then we'll call it quits for this video. Clean a little room up here. Letter D, 9 over 5x squared. And might as well move it up since it's the last one. Again, the 9 and the 5 we can pull out front. 9/5. But what do we do with that x squared? It is in the denominator right now, and it's in the denominator with a positive exponent, x to the positive 2. When we do bring that up from the denominator, we'd have to make that exponent negative, 5x to the negative 2. And now we can take the derivative. So y prime equals, exponent comes down and multiply here by that numerator, negative 18/5 x to 1 power lower. Drop negative 2 down to a negative 3. And to make it look pretty, we'll get rid of that negative exponent. We do have negative 18/5, and that x to the negative 3 will get tucked down there into the denominator and become an x to the positive 3rd. Alright, that's enough for this video. Product rule and quotient rule. Next one we'll get into the trig functions and the higher order derivatives. I can't wait.